share my screen and pop this into presentation mode. Okay, so I can no longer see anybody. I guess my question is, can you see my slides?
Yes, we do.
Yes, we do. Fabulous.
Yeah.
Okay. And you're seeing my main presentation slide, not presenter mode, right?
Yes. Yes.
Okay, fabulous. All right. And if someone, if people join and need to be admitted, actually, I think I can still do that. Yeah, this is actually working fine. So I can admit people as I'm talking. Okay. So the presentation today, entitled Understanding the Early Development of Executive Function. I'm John Spencer. For those of you who don't know me, I'm at the University of East Anglia in Norwich in the United Kingdom. And we'll get started. So to be successful learners who show creativity, flexibility, and discipline, children must acquire a complex set of skills known as executive functions. These skills enable children to mentally play with ideas, to give a considered rather than an impulsive response, and to stay focused. EFs are a really important or key developmental skill for kids to acquire. Why are they important? Executive functions are more predictive of school readiness than IQ, and executive functions predict math and reading competence in the school years. Individual differences in executive functions remain critical throughout life, predicting career and marriage satisfaction and positive mental and physical health. Reversely, children 3 to 11 years with poor executive functions have shown to have worse health outcomes, earn less, and commit more crimes up to 30 years later than those with better executive functions. So simply put, executive function, individual differences seem quite predictive of a lot of important outcomes in development. Now, given that executive functions predict longer-term outcomes, there's been heightened interest in early executive functions, EEFs, which are typically defined as executive functions from infancy to about 3 to 5 years of age. And the reason for this is this might be a critical period in development where we might have the opportunity to do early intervention. And the idea here is if we could ensure that every child has good executive functions by 3 to 5 years, this could have a large societal impact by improving longer-term outcomes, improving health, improving well-being, improving productivity, decreasing criminality. Now, a key challenge that stands in the way of realizing this vision is how to conceptualize early executive functions. So simply put, it's hard to design effective assessment and intervention without a clear understanding of how early executive functions emerge. And so today I'm going to talk about work we've done to try to develop a theoretical framework for understanding early executive functions using dynamic field theory. Now, if you look at the literature on executive function, one of the dominant conceptual frameworks for executive function comes from a Miyake 2000 paper, where they propose that executive functions are a set of higher level cognitive skills that sit on top of and coordinate lower level component skills that include working memory, holding task goals in mind, inhibition, which prevents distraction, and task switching, which is involved in updating goals as the situation changes. And if you look at the developmental literature using this conceptual framework, it's been challenged both at the level of empirical data and conceptually. In terms of data, there's a pretty highly cited study by Wiebe et al. In 2011, where they basically did the same thing that Miyake did with adults, which is have kids do a battery of tasks thought to tap the different components of executive function, like working memory and inhibitory control. And then they did a factor analysis of the resultant data. And instead of identifying 3 factors that mapped onto the Miyake factors, in early development, it looked like a 1-factor model did a better job capturing the data. So that sort of challenged the idea that maybe this 3-factor model is the right picture for data in early development. I think there are also deep conceptual challenges to applying the Miyake perspective in early development. First, executive functions are thought to be a set of higher level cognitive abilities that sit on top of these component abilities. You could really argue, what is higher level cognition from infancy to 3 years? Do infants actually have higher level cognition? And I'm not sure they do. So higher level cognition itself may be something that develops or is a product of development. And then there's a conceptual challenge as well. If higher level components are supposed to, or processes are supposed to sit on top of component processes like working memory, how do you think about basically the co-development of executive function with the components themselves? Because we know inhibitory control changes dramatically from infancy to 3 years. We know working memory changes dramatically from infancy to 3 years. So here we have to think about executive functions as essentially co-developing with the components. And that, of course, presents a complex developmental picture. So we've argued, given these both empirical and conceptual challenges, we need a better understanding of what executive function is in early development. So back when this DFT community member was a graduate student in my lab back at Iowa, we started on an executive function journey, and we looked at the literature on the development of executive function, and it seemed like some of the richest data was coming from the use of the dimensional change card sort task. So we decided to see if we can develop a theoretical framework for thinking about what goes into this dimensional change card sort task. For those of you who may be less familiar with this task, children are shown 2 sorting trays with target cards on the trays. So a blue circle over here and a red circle or red star over here. And then they're given cards to sort. And in the first phase of the game, they're given a rule. So they might be told, today we're going to play the color game. In the color game, blue things go here and red things go here. And then they might see a card like this and say, okay, so remember, we're playing the color game. Remember, blue things go here. So where does the blue star go? It goes to the left. Then they might be shown a red star. Where does this go in the color game? It should go to the right. Then that's called the pre-switch phase. Then we go into the post-switch phase where we're going to change the rule. We're going to tell kids, now we're going to play the shape game. In the shape game, circles go here and stars go here. See this? Where would it go in the shape game? Of course, the blue star should go to the right, and the circle should go to the left. What I'm showing you in the data slide here, these are data from a monograph by Zalazo and colleagues. And what you can see, this is age along the x-axis and the scaled score performance in the DCCS task. Higher numbers is better performance. And what you could see is basically pretty rapid development in performance on the DCCS task between 3 and 5 years, and then kind of gradual change from there out into adolescence. Now, the canonical finding with 3-year-olds is that they do just fine in the pre-switch phase. So when given this card to sort, they will sort the blue star to the left and the red circle to the right. But when we switch and play the shape game, they perseverate and continue to sort the cards by color instead of by shape. And then we see rapid improvement between 3 and 5 years. Okay, so Aaron and I came up with a theoretical account of what's going on in the DCCS task using the framework of dynamic field theory. This was published in a 2014 monograph. And what I'm going to do is just give you the quick tour of the theoretical account that we came up with. All right, so the starting point of this theoretical model is to think about cortical fields in different parts of the brain. So we know in parietal cortex, there are cortical fields that are receptive to changes in the spatial position of objects. So we could think about a cortical field shown here on the right side of the slide. The blue line shows the activation in that cortical field at a particular moment in time. Neurons in this cortical field are tuned to spatial positions. So neurons in the middle, like the center of space, neurons on the left, like left, neurons on the right, like right. And what you can see is a little bump of activation on the left and a bump of activation on the right. That's reflecting the presence of the two sorting trays in the DCCS task. Now, when we think about processing of visual features, we know in the ventral pathway, there are cortical fields that are receptive to color as well as the spatial position of objects, and other cortical fields in the ventral pathway that are sensitive to the shape of objects as well as their spatial position. So these are what we call 2D dynamic fields or cortical fields. So their two dimensions are, let's say, the color and spatial position of the object. So you could see a little hot spot of activation in this case on the left. That's reflecting this color value would be the blue hue value. And that's at a spatial position on the left, reflecting the blue thing to the left. And this hue value would be the red hue value. And so this hot spot of activation is reflecting the red thing on the right. And in the shape field, we have a similar pattern where this would be the shape value for circles. So this would be a circle on the left, and this would be the shape value for stars. So star on the right. Okay. Now, critically, we know that neural fields in the ventral pathway and dorsal pathway talk to one another. And so we've used the concept that objects are represented by binding visual features together by virtue of their shared spatial positions. And so the arrows in the brain figure over here are reflective of the coupling in the stack of neural fields we have here. So when there's above zero activation in this spatial field, it'll pass a ridge of spatial activation down to the other two. Similarly, if a peak emerges in one of these feature fields, that will pass activation up to the spatial field, which will pass its ridge of activation back down. So in short, these three fields are coupled together by their shared spatial position. The last piece of the architecture, all right, let me let that person in. Last piece of the architecture was two higher dimensional nodes in our network, capturing aspects of activation of frontal cortex. We had a color node. The color node basically was meant to capture the rules of the game, and we wired up the color node such that it passed stronger activation homogeneously to the color space field and weaker activation to the shape space field, reflecting some mapping or some knowledge that the word color refers to this feature value and less so this feature value. Similarly, we had a shape node that passed stronger activation to the shape field and weaker activation to the color field. As you can see, these are dynamical nodes, so they excite, they influence their own excitation, and they were mutually inhibitory. So these nodes can kind of go into an activation state when you're actively holding a particular rule in mind. Okay, oops, sorry. So this was our implementation of dimensional attention in this model. What I'm going to do is just walk you through kind of step by step how the model behaves as we're going through the DCCS task.
John, real quick, somebody's got a question. Jason.
Yep. Question? Jason? Hello? Finding the mute button or unmuting.
Or maybe
Okay.
this mic doesn't work.
Yeah. So Jason, just chime in if you get your microphone working. I'm happy to be interrupted at any point. Okay. So when we think about performance now in the actual task, the first thing we're going to do in this model is we're going to say to the model, as we do to kids, that we're going to play the color game. So we give a boost of activation to the color node. That then projects a little bit of extra activation to the color space field. Then we're going to present a card. So the way we presented the card in the model is shown here. So the card's features were fed into the model. So we are seeing the blue hue value here and the star feature here. And I'm going to roll back a little bit to the very beginning of the presentation of the card. You can see at the very beginning of the card presentation, that blue hue value is intersecting with the hotspot of activation, reflecting that there's a blue thing on the left. So when that ridge of activation comes in, we can see stronger activation on the left than on the right. So that's basically where that feature is intersecting with the existing activation coming from vision of the target cards in the task space. You can see in the shape field, slightly stronger activation on the right side than the left. That's because the star feature is on the right in the task space. And you can see a little bit of a asymmetry here, right? So stronger activation for the blue hue value and less for the red hue value here. That little asymmetry is actually coming from the boost to the color field provided by the activation of the color node. So that just homogeneously raises activation in the color space field. We get a little bit stronger activation at the red hue value. And the way these cortical fields work is through a local excitation surround inhibition type of interaction. So as activation is growing at this location, it's actually being suppressed elsewhere.
John, the question that Jason had is whether the color and shape representations here are nodes or fields.
So the color and circle, the color node and shape node are nodes. And these are continuous fields over here. Might have another question coming. I'll wait till my translator chimes in here. Or maybe I answered it.
Well, yeah, the next follow-up is, are the nodes coupled to specific locations in the fields?
In this model, the color node projects homogeneously to the entire color space field. So it's basically projecting a single activation value, homogeneously raising or in some cases lowering the activation of the entire field. Okay, and we'll unpack the representation of what color means in a little bit later in the talk. That's an important feature of our newer model. Okay, so in this current state of the model, I've just presented the blue star to the model. Again, blue hue value, star feature value, and then we're going to basically allow the model to make a decision. That's a decision in dynamic field theory. So basically what just happened is it formed a peak in the spatial field on the left. There's a peak at the blue and left position in the color space field. And there's a peak at the star left position in the shape space field. If I roll back just to the moment when that decision is made, you can see it's really the asymmetry between, the blue has a little bit of an advantage here, or the left blue position in this field has an advantage because there's something blue on the left. The blue hue value is being presented, and this field has a little bit of a boost from the activation of the color node. So kind of all those factors combined are what is leading to this peak emerging in this field. Once it emerges in that field, it projects up to the spatial field, right, which then ignites a peak there, which then passes this spatial ridge back down, which then binds the shape feature to the left position as well. So in the end, the model then decides, okay, yeah, we're going to sort that blue star to the left. Okay. Continuing on, we're going to then go into trial number 2, and we're give the model a red circle to sort. What I'm going to do here is just when we do that, we reset the fields in between trials. And when I reset the fields, I want you to notice there's a couple additional features of this model that I haven't told you about yet. So let me just go just a little bit farther here. So the final piece of the architecture that I haven't told you about is that these cortical fields have a memory trace mechanism in operation. So basically, whenever a peak forms in one of these fields, it leaves a memory trace at the associated position, and those memory traces feed back into the field. So the easiest place to see that is here, down in the shape space field on the left. So on the just previous trial, the model sorted a star to the left. And so this is the star feature value. And you can see there's a faint, I don't know if you could see that on your screen, but there's a faint activation profile here that reflects the memory trace of having sorted the star to the left on the just previous trial. Similarly, you can see in the color field that the hotspot at the blue left position is a little bit more intense than the hotspot at the red right position. That's because there's a memory trace that you just sorted a blue thing to the left. So these memory traces, again, just accumulate from trial to trial to trial and feed back onto their associated cortical field. Okay, rolling forward, we now are going to give the model the red circle card to sort. Pause that. Go back and do that a little more slowly. So here's the red hue value comes in, the circle feature value comes in, and the model's task is to figure out where in space those features should be sorted. If I roll forward a little bit, you can see, again, there's a stronger activation on the red versus on the right, the red right position than the red left position. That's because there's a red thing in the task space. So again, we're seeing that asymmetry in color playing a role. And as we roll forward, we're going to see that the model forms a peak of activation on the right side, reflecting its decision to sort the red circle, so red circle to the right position. So we're going to let that play out. Sorts it to the right. Okay, so in the DCCS task, we'll typically do 6 pre-switch trials. And so what you're seeing here is the state of the model at the end of the pre-switch phase. What you can see is there's a nice little hotspot of activation for the blue feature on the left and the red feature on the right. That's because it's been sorting by color on all the pre-switch trials. So what you're seeing here is a combination of a strong memory trace for those features and those positions, combined with seeing the blue circle and red star out in the task space. So we talk about this as we're seeing cooperation in the color field, because the perceptual features of the task cooperate with the memory traces. Down in the lower field, you can see we have competition. So the model has a memory of sorting the star to the left repeatedly, but it's seeing a star to the right in the task space. Similarly, it has a model or memory of sorting the circle to the right repeatedly, but it's seeing a circle at the left position in the task space. So cooperation here, competition here. Okay, so now we come to our developmental account in this 2014 paper. We propose basically that the young model perseverates because its representation of the dimension color and the dimension shape
Yeah.
have not yet evolved over development. So basically, the shape node has a stronger projection to the shape field than the color field, but it's not completely cleaned up in development yet. So what we proposed is that developmentally, what's happening is the connectivity between these dimensional nodes and these posterior cortical fields is becoming more refined over development, such that later in development, shape projects more strongly to shape and more weakly to color, and color projects more strongly to color and weakly to shape. All right. What I'm going to do now is just jump to some quantitative simulations of this model, showing that it captures data from the DCCS task. I'm showing you the state of the model at the end of the pre-switch phase for reference to the previous slides. And that'll help us understand some of the effects as we move from DCCS task to DCCS task. So when we simulated the model in the standard DCCS task, which is shown here on the left, so you can see the same arrangement of what I was just walking you through, with the blue circle on the left and the red star on the right. And in the post-switch phase, we just it's the same type of cards. The only thing we do is say, now we're going to play the shape game. Okay. And what you can see is a low percentage of 3-year-olds switch to the shape dimension, and a high percentage of 4-year-olds switch to the shape dimension. And what I'm showing you are simulations of the model in blue and data from the literature in red. And you can see a good quantitative match between the two. Again, what's going on under the hood here is we're changing two things in the older model. We're cleaning up the connectivity between the nodes and their posterior cortical fields. So again, for example, shape maps more cleanly to the shape dimension. We also changed the strength of interactions between the nodes themselves. So their excitation is stronger and their mutual inhibition is stronger. So when we implement those changes, we could see that the 3-year-old model perseverates and the 4-year-old model succeeds in this task. Importantly, the model can generalize across different variants of the task. So for example, this is one of the, another example from the literature. This was a study designed to probe if maybe the dimension that kids are switching to could be, sorry, the dimension they're switching from is part of the problem. So as you can see in the negative priming version, kids play the color game with the standard set of cards. And then when we switch to the shape game, we actually change the colors. So the idea is maybe the color representation from the previous phase is having an influence on the post-switch phase, and that's part of the problem. As you can see, that doesn't exactly fix the problem. So 3-year-olds still tend to perseverate and 4-year-olds still tend to succeed. That's the case in our model as well. And of course, we can dig into the model and ask why. So shown here in the middle of the slide is the model at the end of the pre-switch phase, just like before. And what you can see is when we change the colors in the post-switch phase, what that does is that gets rid of the cooperation, but it doesn't get rid of the competition in the shape field. So if we give a boost to the shape, the shape node in the post-switch trials, the model still has to overcome this conflict. And as you can see, the model still tends to perseverate when we have the young model. Okay, so just changing the cooperation isn't sufficient to get the model to succeed in this case with the young settings. Here's another example that did the reverse in the literature. So instead of changing the colors in the post-switch phase, here they're changing the shape in the post-switch phase. And what you can see, if we look at the model, the cooperation in the color field is now still consistent, but now we've gotten rid of the competition in the shape field, again, by changing those feature values that are present. And what we see is that the model and the kids do just a little bit better, but still the model has to overcome this, this cooperation, and the model has a hard time doing that. So again, just changing one of these aspects of the task doesn't seem to be sufficient. That, of course, raises the question, what if we change everything? So here's the total change version. So pre-switch phase, kids maybe sort by color. Post-switch phase, now we change both colors and shapes. As you can see in the model, that gets rid of the cooperation. It also gets rid of the competition. And now the model and kids both tend to succeed in this version of the task. Okay, there was also one other version of the task that we encountered in the literature where young kids do a pretty good job, and that's this no conflict standard version. The key trick here is in the pre-switch phase, the target cards and the test cards match completely. As you can see in the model at the end of the pre-switch phase, we've got cooperation now in both dimensions. And so with that state of affairs, just a small boost to the shape field is sufficient for the model to now switch rules and sort by shape. And that seems to be the case with kids as well. Okay, so just to summarize, this is a summary slide from all the different quantitative simulations we did in this 2014 monograph. In summary, we simulated results from 14 different conditions using the same model with the same parameters, total of 37 data points, lots and lots of simulations. Key take home here is that the model was within 0.06 6% of the empirical values across all these 14 different conditions. So it does a really nice job of integrating and summarizing a pretty large literature from this DCCS task. Okay, so this model then captures more data than any other model in the literature. We've also tested novel predictions of the theory at the level of both behavior and the brain. I'm not going to go into those because I'm going to focus on some newer work. But in total, we feel like this is a pretty successful model. So that's where the baby with the fist bump comes from there. But of course, there's limitations, and that's what I want to turn to now with the remainder of my talk. So when we were doing this work, we kind of identified two directions in which the theoretical framing was pretty minimal. The first direction was kind of the lower level grounding of the theory in space. And for example, we've done a lot of work on dynamic field models that do visual exploration and learn by visual exploration. None of that is currently present in this executive function model. Similarly, the higher level representation of words is quite minimal in this version of the model. So we kind of viewed it as our initial starting point for what would a theory look like. But we wanted to then explore, could we extend the model in both of these directions? In particular, Aaron's done a lot of work on this question of what do we know about the higher level representation of words and the emergence of executive function, focusing in on dimensional attention. So his work looks at dimensional attention, how the word color maps to the hue dimension. That's of course a central issue in this model of the DCCS task. Data from this literature show that initially, children seem to learn individual color labels, like the word red, the word blue, the word green, although they don't always use those labels correctly. Then they seem to understand or learn that the word color refers to these individual labels. So when asked to produce a quote-unquote color, children will pull out a word from the correct class and respond, let's say, red, blue, or green. And then eventually children sort the mappings at both the individual and that dimensional level. So at the same time as kind of these discussions were ongoing about expanding the picture of the model, and Aaron was doing this wonderful work on how children learn color words and what the dimensional label color means. In parallel with that, Larissa Samuelson and I had developed a dynamic field theory of early word learning called WOLVES, which stands for Word Object Learning via Visual Exploration in Space. The best acronym we've ever come up with, I think. So we're very proud of the acronym. This is a picture of the architecture. And so, Aaron's data over and over kept pointing to the idea that as kids sort out what these individual color labels mean and what the word color means, for example, that was changing how they perform an executive function task. So we had this interesting idea, maybe we could think about executive function in the context of our word learning model, and that might guide us toward an expansion of the initial model of executive function. So the word learning model itself captures a lot of really interesting data. That model has been anchored to studies of cross-situational word learning, which I don't have time to go into, but it does a nice job of capturing data from both adults and younger kids, as well as proposing what is changing under the hood as kids get better and better at word learning. So for those of you interested, I'll point you to the psych review paper in case you want to check in on some of those details. But I'm going to focus instead on a recent developmental review paper that we wrote. And the central question that we embarked on was, can we take this model of early word learning and see if it sheds new light on our understanding of how word learning and executive function go together in early development? So concretely, we asked, could wolves capture children's performance in the DCCS task? And if so, could it also shed light on how children use and learn color words and dimensional labels? So kind of bringing together these literatures on the learning of dimensional labels and color words, for example, as well as executive function tasks. So we had a number of goals in this paper that we laid out. The first was very simple, which is just to see if we could get this model to capture performance in that DCCS task. And we wanted to do that in a particular way, focusing in on the developmental question. So basically what we wanted to do is create a version of wolves with weak dimensional label learning. So kind of initial stages of learning what these color words and the word color might mean. And then a strong dimensional label learning, where the model has a strong representation of, let's say, the individual mapping between a color word and its hue value, as well as the mapping between the word color and all these individual color words. So we wanted to see if we change just the word learning part of the model, would that explain and capture data from the executive function tasks? If that was possible, then we wanted to see if we could also ask wolves to do the language tasks that Aaron has probed in his lab, which include data on the comprehension and production of dimensional labels, as well as color words, for example. Then if we could do that, we wanted to ask, could we quantitatively reproduce findings from all three tasks? And then if we could do that, we asked, are there any additional data we could explain with the new model that we couldn't explain with the old model? And then if we could do that, the final question was, did we break wolves? So does wolves still do cross-situational word learning, which was kind of the home word learning type of task that we had probed with the wolves model? All right, so we had a lot of goals in this task. I'm going to just kind of run you through a summary of what we discovered in this paper. Okay, first thing, and let me orient you to this now more complicated neural architecture. All right, what you're looking at, if you think about the previous architecture, what we had was a shape field, a space field, a color space field, and a shape space field, all stacked up together. That's living in the middle part of this model right here. So this is the spatial dimension. So these neurons are tuned to space in the frame of reference of the scene. So neurons here like items over on the left, neurons over here like items on the right, just like before. Here we have a color space field. You can see the color dimension labeled over here on the far right. And we have a shape space field. You can see the shape dimension labeled over here on the far right. So this stack of fields is essentially operating in a very similar way to the previous model. And when this stack of fields makes a decision, meaning forms a peak at, let's say, the rightward position, which color is at that rightward position and which shape is at that rightward position, that's going to mean the same thing. So that's going to be a decision to sort the card to that position in space. Okay. The front end of the I should say, why is it front end? So when we present this model, usually you often maybe think about the visual input to a model as being maybe on the left side because we read left to right. We put it on the right side to reflect essentially brain anatomy. So if you think about this figure is oriented with the frontal part of the system over here on the left, and the visual field or cortical visual fields in the back part of the model, which is in the back of the brain. So that's why the visual field is off to the far right. So we have visual fields here. This is now situated in the space of the retina, and these would then be visual fields that are sensitive to the hue values present on the retina. So this would be, I'm seeing something red on the right side of my visual field, and this would be I'm seeing something blue on the left side of my visual field, and that reflects the target cards in the task space. Similar down here for the shape field, I'm seeing a star on the right, and I'm seeing a circle on the left. In the middle of between the visual fields and what we call the scene level attention fields here, we've got an attention, a contrast, and a working memory layer. This is borrowed from our visual exploratory model. I'm not really going to talk about the details of that today, but you'll see kind of those fields operating in the simulations I'll show. Working now to the middle part of the figure, we've got a scene representation that the model builds. So a working memory for which items are where in the scene. So as the model visually explores the item on the left and the item on the right, it's going to build a scene representation that there's a red star on the right, which in fact there is if you look up here. And there's a blue circle on the left, which is what's in the task space on the left. So we're going to see memory traces build up, which is our kind of longer term representation of this particular scene we're looking at. And then working memory is going to be the currently active items that we're seeing or activating in our scene representation. Finally, on the far left of the model is our kind of frontal system. We've got what we call word feature fields. So we're going to have a word dimension up here. These are just discrete nodes for each word that the model knows. And when a node comes up here, it'll send a ridge of activation down here, which represents the mapping between that word and its feature representation of items in the world that it's seeing. That feature representation or word feature mapping is shown here. These are longer term memory fields. So this is basically like our semantics for what the words mean. So you can see I've got a bunch of little Gaussian representations. These are all the individual words that the model knows. So this would be the word for red, and down here would be the word for blue. And then over here are the different shape words that the model knows. So this would be the word for star feature. This would be the word for circle. Okay, so that's just trying to orient you to the architecture of the model. I'm going to kind of walk through a number of simulations to show you the model in action. I can tell you up front, we had to make one change relative to the original Wolves model. And that change is highlighted by the green arrow. So we added an excitatory projection from the word feature field to the working memory, scene working memory fields. The reason we needed that is we needed some way for the word representations to influence what's active in my scene representation. So that when I, let's say, think about the red thing, we needed a way for the red thing to influence my representation of all the red things in the scene. Okay, now it's a very sort of natural type of connection to think about. Interestingly, we didn't need that connection in the original Wool's work on cross-situational word learning, but it is added in here. Okay, so now I'm just going to walk you through the model kind of in action, doing the DCCS task. We're going to start with the old model, and then I'll show you the young model perseverating. I'm going to do this at a pretty high level because there's a lot of details here I don't want to get bogged down in. So the first thing, just to highlight, I mentioned this already, but the older model, which is what I'm going to start off with, had a nice clean representation of the color words and its shape words. So a nice one-to-one mapping between, red means this particular hue value and blue means this particular hue value. We're going to make that this representation messier when we go to the young model because kids haven't quite worked out the mapping between their color words and hue values earlier in development. Okay, so we're gonna one of the interesting things when we first started simulating this DCCS task is that we had to think about how to implement the instructions. So just like we have to teach kids how to play this card sorting game, we have to teach our model to play the card sorting game as well. And that's actually an important component of how the model starts to represent what where these objects should go in the task space. All right, so we start by teaching the model how to play the DCCS task, and we say, okay, we're going to play the color game. And our representation of the word color is going to be to activate all the color words that the model knows. So when we say that we're going to play the color game, it activates all the color representations that it has. And we're assuming that it, through development already, we've learned that mapping from the word color to all the individual color words. So we're going to play the color game, and in the color game, red things go here. So we give the model the input red. That passes this ridge of activation down into the word feature fields. It then recalls that the word red maps to this particular hue value. That sends a ridge of activation this way. It's also seeing a red thing, and we've highlighted the red things go here. So we give it a spatial input at the right location in the retinal frame of reference. And basically then the model sort of mentally decides, yeah, that red thing, which happens to be a star, goes to the right. We do that then, in the color game, red things go here, and we do blue things go here. And then we give the model a card to sort, and we say, where does this go in the color game? So you can see we're still activating all the color words because we're playing the color game. We give it a red thing to sort, so it's attending to the red circle. And what we can see is that the model then says, yep, okay, the red circle, that's going to go over there on the right because it matches that I am seeing a red thing in the task space on the right side. The green oval is just highlighting that on the previous trial, the model had decided that the blue star goes to the left because it matches the blue thing it's seen on the left. And I'm just highlighting here that there's a memory trace in this model, right, just like before. And you can see that it's binding the blue and the star thing together to the left position, which is where they go in the task space. So you can kind of start to see already from the instruction phase that we're in the same ball game with this cooperation and competition story. So in our scene representation, after the instruction phase, we've got cooperation in this memory trace field where red things have consistently gone to the right, and we're seeing a red thing on the right. Whereas we're getting competition in the shape field, we're seeing a star on the right, but we have a memory of sorting stars to the left. Okay, so immediately you can see aspects of the previous theoretical account coming to the foreground in this more complicated model, just by embedding the model in the rules and instruction phase of the task. Okay, so then we give the model a card to sort. We present that in the middle of the retinal frame. We say, okay, we're still playing the color game. Where does this go in the color game? So the model sees that it's a blue star, projects these feature ridges across the architecture of the model. That intersects, the blue intersects with the representation of the word blue. So the hue value blue intersects with the word blue, and the model says, oh, that's a blue thing. This peak then projects back into the working memory. It activates all candidate blue things in the scene representation. It's got a memory that blue things, or a working memory that blue things are on the left. And so the model decides to sort that card to the left. Now, I just want to highlight, in the paper, we're showing a simulation. This is a static simulation, unfortunately. But this is at the moment of the decision. Once that decision starts to build on the left side, a peak emerges here. That drives a peak in the spatial field just like before. You get coupling just like before. It builds a peak here at the star feature value. And essentially, it's operating just like the prior model at that point. Okay, so the old model sorts correctly on the first pre-switch trial. You can see it actually sorts correctly on all the pre-switch trials. Then we go into the post-switch trial, and we first need to give the instructions to the model that we're going to play the shape game. So we say, okay, now we're going to play the shape game. So we activate all the shape words. In the shape game, circles, so we activate circle, go here, and we give it the left item. Okay, so it activates circle, and it learns that the blue circle goes to on the left. Okay, so then we can you can imagine, and here's the simulation just showing you the first post-switch trial. So now we give it a red circle, so red and circle. Those features then project across the architecture of the model. The circle feature intersects with the representation of the word circle. It says, okay, that's a circle. These features then fish out the associated features in the scene representation. And the model decides to sort the red circle to the left, which is the correct location. And then that iterates through the 6 post-switch trials, and the old model does quite well. All right. So what happens in development? So what we're going to do in development is we're basically going to change. The only thing we're going to change is the representation of the words. So you could see the representation, instead of being kind of that nice crisp diagonal that I showed you previously, you could see the activation of the diagonal is weaker. And in a number of cases, we've got a competitor representation. So this would be the case, let's say down here. Let me take this one. So this is the blue hue value. The model's got a pretty decent representation that hue value maps to the word blue, but it also kind of thinks it maps to the word red, which is this guy. So it hasn't quite figured out, is that hue value blue or red yet? Similarly, you could see some confusions for the shape words as well. All right. So the only thing we're changing in the model is the representation of the words. So then we're going to run the simulations in the same way. So we're going to teach the model how to play the color game. So in the color game, red things go here. And actually, this is a part of the, sorry, this is a trial where we're giving the model a red circle to sort. And I'm showing you that it fishes out the word red. It finds red things in the scene representation, and it decides to put the red circle to the right, which is the correct response. So, and that's actually reflecting what 3-year-olds do as well. They're quite good on the pre-switch trials. Here's an interesting simulation that shows that the model can still sort correctly on the pre-switch trials, even when it activates a representation of the wrong word. So in this case, we gave the model a blue star to sort. Features are passed across the architecture of the model. And what you can see here is at the blue hue value, it's got a kind of conflicting representation of 2 words. And in this case, instead of activating the word blue, it activated the word purple. So it activated the wrong word representation, but this peak in the word feature field still goes in and fishes out all the blue-hued things, even though it's thinking purple, because it's seeing the blue hue value. So it fishes out all the blue things and decides correctly to sort the blue star to the left. So that was an interesting example where, you know, even if young kids aren't necessarily retrieving or recalling the correct word, they can still sort correctly in the task. Moving now to the post-switch trials, I'm showing you early and late in the post-switch trial for the young model, just to kind of unpack what's going on and why the model perseverates. So here we're now playing the shape game. So we activate all the shape words. We give the model a blue star to sort. The feature ridges project across the architecture of the model, intersects with a representation of blue because it's just sorted a bunch of blue things. So it's trying to build a peak here, but you can see it doesn't activate any of the color words because we've told it to play the shape game. In the shape game, it's only going to ever activate shape words. But it's thinking about the blue hue value because of the pre-switch trials and its bias for the blue thing. And what happens basically is the activation builds sufficiently in the word feature field that it builds a peak here at the blue hue value, fishes that out in working memory, and it actually decides to sort the blue star to the left, which is the incorrect response. The blue things were supposed to go to the right. Now, interestingly, you'll notice that it does eventually activate that the thing it's seeing is a star. Okay, so it does actually activate the correct word representation, but it sorts by color in its sorting behavior. Okay. Complicated model, I know, but I just wanted to give you a sense for kind of the backstory and why it works the way it does. Here's the quantitative story. As I said earlier, I highlighted we added 1 new connection in the model. That's why we're calling it Wolves 2.0. We did change some parameter values for all tasks that we simulated. And we have had to modulate a couple parameters across tasks, and I can highlight or talk more about that in the discussion section if people are interested. Here, I just wanted to emphasize that the Wolves 2.0 does quantitatively simulate behavior from the DCCS task. So here's data from behavioral studies in the literature and the model's performance on the DCCS task. We also placed the model in Aaron's production and comprehension tasks. Again, we changed the strength of the representation of the words for the old and young models. And what we see is that the same model that captured performance in the DCCS task does a nice job of reproducing behavioral performance from the production and comprehension tasks. Real briefly, in the production task, the model is shown an object, and we might say, what color is this? And they're supposed to reproduce the color label. And in the comprehension task, we'll give them an array of items, let's say on the screen, and the comprehension task says, find the red one. Okay, so just so that's clear. I do have a couple simulations, but in the spirit of having time for discussion, I'm going to skip over these. Just briefly, let me mention, there was when we were doing this work, reviewers asked if we could simulate anything new with Wolves 2.0 that we couldn't do with the original executive function model. And Aaron dutifully went back to our 2014 paper and found we talked about this Yury's and Munakata 2006 paper in our monograph, and discussed how the 2014 model couldn't capture these data because these are variants of the DCCS task where they changed the nature of the labels that they used. For example, in the novel feature version of the task, they would say things like, we're going to play the shape game. In the shape game, daxes go here and wugs go here. So they changed the individual feature labels. Now that we have a model that actually has those labels actively represented, we were able to simulate performance from the Yury's and Munakata paper. Here you can see the blue bars are the empirical data across these different conditions where they varied the nature of the labels used in the task. And the orange bars are from Wolves 2.0, and it did a nice job of capturing data from those conditions. Again, happy to talk about in more detail in the discussion. And then in the last step, we asked, did we break Wolves 2.0, or do we break Wolves, or does it still do cross-situational word learning? So we re-simulated a number of the developmental cross-situational word learning studies we had simulated in the psych review paper. And basically what we found is that for some simulations, Wolves 2.0 was either the same, sometimes it was a little bit worse, sometimes it was a little bit better, but overall the quantitative fit to the data was actually pretty good across the board. Okay, let me just now turn to some discussion. So first of all, some evaluation of what we've accomplished. Wolves 2.0 integrates lower level visual exploration, including visual attention and visual working memory, with higher level processes of word learning and dimensional attention that are central to early EF tasks. So as we said, we tried to expand the model into lower level visual exploration and then unpack the higher level representation of the model as well. Seems to capture a lot of data with pretty good generalization across tasks. Although I think one of the things Aaron's going to talk about in March is some of the limitations that we've run into by trying to simulate new things with Wolves 2.0. Of course, the limitation, it's a very complicated model. And I could say we've got even more complicated versions up our sleeve that we're considering. So, as you try to capture more and more phenomena, the models inevitably become more complicated. And that's, of course, the barrier to understanding and things like that. Thinking about kind of taking a step back to where I started with executive function, I think one interesting question you could say is, where are the components of executive function in our model, or are there components in our model? And here's just a couple of examples to say I think this model challenges the component picture of executive function. So if we start off with one component that's supposed to be important for executive function, which is inhibitory control, you could say there clearly is neural inhibition in our model, right? That plays a key role in avoiding perceptive responses. So for example, the way the old model works is it recalls the word feature mapping, let's say for the word circle, and this then blocks the word feature mapping for the word red that was built up during the pre-switch phase. So inhibition is doing the job of suppressing the perseverative tendency in the model. But importantly, there's not a specific inhibitory control module that's doing that. That's emerging from the excitatory and inhibitory dynamics within a neural field in a particular part of the architecture. So I would say, there's not an inhibitory control component per se. Just as a second example, we could think about attention as, some people have proposed attention as a critical component of executive function. If you think about attention in our model, basically that means any cortical field that has winner-take-all dynamics. So that makes a selective decision. I'm going to build a peak here rather than anywhere else in the field. And there are actually 4 different variants of attention in the model. There's a spatial attention field. There are feature attention fields. There's a top-down word-driven type of attention, and there's dimensional attention. So again, attention's not a module in the model. It's actually an activation state and the kind of behavioral or neural consequences of that activation state. So I think, when we unpack how kind of a neural architecture like this works, we don't get these neat, tidy components like inhibitory control and attention. Instead, we get sort of emergent executive function behaviors from the way information is processed in this neural system. Again, returning to some themes from my introduction, you could say, looking at this model, what is higher level cognition from infancy to 3 years? Does it give us any insights into that? And I think when we think about what is executive function in this model, it's really about learning dimensional labels and applying those labels to guide dimensional attention to specific features flexibly in the world. This, of course, means you have to learn about individual word feature mappings. You have to learn what dimensional labels are and what they mean. And then you have to activate, the right set of word feature mappings at the right time and the right context to find the task relevant features in space. So kind of more generally, we could say executive function is about, kids have to learn which features of the world are the ones I should attend to in order to regulate my behavior in this particular context. So when I'm sitting there at story time listening to the teacher read the book, I should be attending to where the teacher is, to the story, to what she's saying, and I shouldn't be attending over here to my mate who happens to be talking to me. So kind of good executive function is learning those mappings and applying those mappings in context. And then the last challenge I posed in the beginning was, how do we think about development when those higher level processes that we call executive function and component processes like working memory are changing at the same time? And I think that's a really tricky thing to think about, but I think Wolves 2.0 gives us a framework for thinking about how we might understand how these lower level components and these higher level processes co-develop. And I'll just leave you with a picture that we've been kind of contemplating on how that might happen. And it's really a picture of kind of cascading changes over development. So we think in infancy, infants are largely working on visual exploratory things, which are captured in the kind of early parts of our model. Early visual fields, shifting attention to different features, shifting attention to different locations in space. Then they start to work out how to map those representations beyond a retinal frame into a scene representation to know what is where in space. That then helps them ultimately to map words to objects as they start to develop more stable scene representations. That helps them figure out what features of words are critical to what those words mean. And then eventually we start to get into higher level cognition, which in this particular framework looks at things like word mappings, how they, learn that the word color, for example, maps to all the individual color labels and not to words for shapes and things like that. Okay, I'm gonna end there to leave some time for questions. And yeah, thanks for your attention. Any questions? You're happy to just kind of come on the mic, that would be great. I can also click on the chat and see if. Maybe I'll actually stop the recording so that.
Or maybe, John, I think I could thank you very